to start out with the definition today. A set of functions f1 of x, f2 of x, all the way up to fn of x is linearly dependent on some interval I if, do you know what that symbol means? There exists. So if there exists constants C1, C2, all the way up to Cn that are not all 0. So some can be 0, but they can't all be 0. Such that C1 f1 of x add all the way up to Cn fn of x equals 0 for all x that are in that interval. A set of functions is linearly independent if they're not linearly dependent. I know, great definition. The linearly dependent one is the most important. Sometimes you'll be able to tell just by looking at the functions. Sometimes you won't be able to, so we'll look at a few examples. Okay, so what that leads us to, if your functions are linearly dependent, let's just look at two functions. So let's say that you have two functions that are linearly dependent. That means that C1 f1 of x plus C2 f2 of x equals 0. C1 and C2 cannot both be 0. If we solve for f1 of x, we get negative C2 f2 of x divided by C1. This negative C2 over C1, that's a constant. So what's very important here is that f1 and f2 are constant multiples of each other. Okay, so what does that tell us? It tells us that a set of functions is linearly independent when neither is a multiple of the other. First example, let's consider two functions. f1 of x is cosine of 2x. f2 of x is 1 minus 2 sine squared of x. I want to know if these functions are linearly independent or linearly dependent. Okay, looking right away, they're not constant multiples of each other right this instant. Is there a way that we can re-express that cosine of 2x? Okay. So there is the 1/2 times the quantity 1 plus cosine of 4x. That's not helpful here, though. Is there any other identity? How about 1 minus 2 sine squared of x?
That's a good one.
That is a good one. Okay. So then we would say f1 of x and f2 of x are linearly dependent Okay, you cannot just write because they're constant multiples of each other. You have to go back to the definition. So C1 f1 of x plus C2 f2 of x equals 0 when C1 equals something, C2 equals something. What does C1 equal? Or what do they have to be? How about just -1 and +1? Okay. We with me so far?
Instead of f2 of x, 1 minus 2 sine squared x? Or,
Yes.
oh,
Yeah, that's a exponent. Sorry if my handwriting is messy. Okay, example number 6. f1 of x is equal to just plain old x. f2 of x is equal to absolute value of x. I want to know if these are linearly independent or linearly dependent. Now, in this case, it might be helpful to look at their graphs and see if that gives us anything. So that's what I'm going to do. So f1 of x is a line. f2 of x, absolute value, is the v. Okay, is there anything that you're going to multiply this line by? Any way that you're going to transform it to get a v? No, definitely not. So right now, we can say that the two functions are linearly independent on the interval -∞ to infinity. So if we look at all real values of x, our two functions are going to be linearly independent. Is there a way that we can restrict the domain or the interval to make the functions linearly dependent? Right. So if you look from 0 to infinity or -∞ to 0, our functions will be linearly independent, or linearly dependent, rather. So if we restrict the domain to -∞ to 0, or 0 to infinity, now our two functions will be linearly dependent. Okay, it's important to know you're not always going to have two functions. Sometimes you're going to have more than that. So we just are looking at the cases of 2, but sometimes you'll have 3, 4, 5, etc., more functions than that. As you can see here, this is not really a practical way to go about figuring out linear independence or linear dependence. When we looked at example 5, we only could figure that out when we found C1 and C2. So we need to figure out a faster way or a more efficient way to determine if functions are linearly independent or linearly dependent. And that's where the Wronskian comes in. Wronskian is going to be a criterion for linearly independent functions. So ultimately, that's what we're going to care about in this unit, is finding linearly independent solutions, and eventually you'll figure out why. But this will be a more efficient way. So what we're going to do is I'm going to tell you what the Wronskian is. We're going to prove why that proves linear independent functions, and then we'll calculate the Wronskian a few different times. So suppose that we have functions f1 of x all the way up to fn of x, and that all of these functions have at least n-1 derivatives. If the determinant of the following matrix It's going to be f1, f1 prime, f1 double prime, all the way up to the n minus first derivative. This will be f2, f2 prime, f2 double prime, etc. All the way up to fn, fn prime, all the way down to the n minus first derivative of f of n. If you just take the determinant of that matrix, and it is not 0 for at least one point in our interval I, so not every point, but at least one point, then we say that our functions f1, f2, all the way up to fn are linearly independent. This determinant is called the Wronskian. The notation for a Wronskian is the W, and then f1 of x all the way up to fn of x. That's the notation for a Wronskian. Okay. Before we actually use the Wronskian, we're going to prove why this is the case. We're going to do something called a proof by contradiction. Do you all know what a proof by contradiction is? Have you guys done a proof by contradiction before? Maybe not. Okay, so here's the way that a proof by contradiction works. What you're going to assume is you're going to assume all the regular stuff from your theorem, but you're going to make the opposite conclusion. So you're going to say, let's suppose that we have all of these functions and we have this Wronskian that's not 0 for at least one point, and that the functions are linearly dependent. And then what you have to prove is that that can't be the case, that it's impossible. We're going to do the simple case of n equals 2. You could do n equals higher than 2, but it's going to be the same idea. So let's suppose n equals 2 for simplicity. And the Wronskian of f1 of x and f2 of x does not equal 0 for some x that's in the interval. So we're assuming all this stuff. Now here's where we're changing it. We're going to do the opposite. So and that f1 and f2 are linearly dependent. So again, this is the way that a proof by contradiction works. What we have to now prove is that this is impossible. It's impossible for our Wronskian not to equal 0 and for the functions to be linearly independent. Okay, so if our functions are linearly dependent, here's what that means. There exists some C1 and C2 such that C1 f1 of x plus C2 f2 of x equals 0. Okay, now what we're going to do is we're going to take the derivative. So this will give us C1 f1 prime of x plus C2 f2 prime of x equals 0. So this is a system that we're going to need to solve. Now, here's what we should notice. Because our functions are linearly dependent, we already saw that that means that f1 of x and f2 of x are constant multiples of each other. Okay. Therefore, our two equations are constant multiples of each other. So, our system has infinitely many solutions. Okay. We are eventually going to have to look at the Wronskian. That has to come into play here somewhere. We're going to need a little side review, though. So we're going to leave this proof for a minute. We're going to review Cramer's rule. No? Some of you are looking at me like you've never heard that before. Have we heard Cramer's rule before? No? Okay, so maybe it's not a review. Maybe it's new. Okay, Cramer's rule is another way to solve a system. So let's say that you have a system ax plus by equals c, and dx plus ey equals f. Here's the way that you find x. In the denominator is the determinant of the matrix that contains all the coefficients. So a, b, d, e. In the numerator, the x coefficients you replace with the answers, and then you keep the be. Y then is a similar idea. Denominator is the determinant of the matrix that has all the coefficients. In the numerator, replace the coefficients on y with your answers. Okay. Here's why this is important. If a solution exists, that tells us that the determinant in the denominator is not 0. If the determinant in the denominator does in fact equal 0, there is either no solution or infinitely many solutions. You have to solve some other way. Okay, so that was our side review. And let's go back to our proof. Now remember, we are trying to find C1 and C2. Ooh. So if we wanted to find C1 using Cramer's rule, and the denominator is going to go the coefficients, so that would be f1 of x, f2 of x, f1 prime of x, f2 prime of x. In the numerator, it would be 0, 0, and then f2 of x, f2 prime of x. Now, what we already determined, though, is that our system has infinitely many solutions. We wrote that right before Cramer's rule. If the system has infinitely many solutions, the determinant of the denominator has to equal 0. So we know that the system has infinitely many solutions. So the determinant in the denominator equals 0. The determinant that was in the denominator was f1 of x, f1 prime of x, f2 of x, and f2 prime of x. We know that equals 0. Why that's important is this determinant is the Wronskian. This is a contradiction. So here, in the very beginning, we said the Wronskian does not equal 0 for at least some x. We have now shown it cannot be the case that the Wronskian does not equal 0 and f1 and f2 are linearly independent. This is a contradiction, therefore f1 of x and f2 of x must be linearly independent. Okay. Do we understand the idea of a proof by contradiction? Yes. Alex?
Can you go back to the part where you showed that the system has no solution?
Yes. Maybe, if I can find it. Alex, I really have no idea where I wrote it, so. I used too many pages. We know that f1 and f2 are constant multiples of each other. Therefore, our equations are constant multiples of each other. Therefore, the system has infinitely many solutions. Wasn't that a good proof? If you guys are lucky, we're going to get to another proof today also. That was our first. So was that something you guys had never seen before, Kramer's rule? Yeah, that was new? It's vaguely familiar? Okay, Alex, can I move on? Great. Okay, this leads us to a corollary. If f1 of x all the way up to fn of x are linearly dependent, then the Wronskian of all of those functions is going to equal 0 for all x that are in the interval. Okay, you should be able to do the following. Given a set of functions, you need to be able to tell me if they are linearly dependent or linearly independent. You need to be able to provide evidence. If the functions are linearly dependent, you need to be able to find those constants. So the C1 and C2 and however many C's there are. If linearly independent, you need to show me that the Wronskian does not equal 0 for at least one point in the interval. Okay. Questions on the Wronskian before we actually do an example? F1 of x is 2, F2 of x equals x. Okay, just based on looking, do you think that these are linearly independent or linearly dependent? What?
Independent.
Yeah, they're going to be. You can't tell me because they look like they're linearly independent. You have to do the Wronskian. So that's what you're going to do. Please use good notation. The Wronskian is not the matrix, it's the determinant of the matrix. It needs to be a vertical bar, not a bracket. So you put f1 of x, f2 of x, take the derivatives of both, and then calculate that determinant. So we get 2 minus 0, which is equal to 2. What you care is that that does not equal 0 for at least 1 point. So here it's not equal to 0 for all points. All we care about is there's at least one x. So this then would prove that f1 and f2 are linearly independent. Okay. How do we feel about the Wronskian? It's not bad. You will have to find the Wronskian of 3 functions. Do you guys remember how to find the determinant of a 3 by 3 matrix?
Yes.
Okay, great. Okay, that linearly independent and linearly dependent is incredibly important. And it leads us to this next definition and this next idea. Okay, next definition. A set of linearly independent solutions y1 all the way up to yn for a homogeneous linear differential equation on some interval I is called a fundamental set of solutions. I forgot to remind you, everything we're talking about right now is for homogeneous linear differential equations. Tomorrow we'll get to the non-homogeneous ones. All homogeneous linear differential equations, so that was what I labeled as star 1, they all have a fundamental set. Okay, here's why that's important. If you have this y1, y2, all the way up to yn, and they do form a fundamental set, by the superposition principle, we said we can make an even larger solution, y. That's c1, y1, all the way up to cn, yn. By the superposition principle, we could add them all up with constants and make an even bigger solution. That solution y is the general solution. So we talked about that's what we really care about. We don't care about the trivial or the singular solutions. We care about the general solution. So if you have some solutions that you know and they form a fundamental set, that then can help you form the general solution. Okay. Here's how this is going to look. Let's say that we have the differential equation y double prime minus 9y equals 0. And we know that this possesses the following two solutions. y1 is e to the 3x, and y2 is e to the negative 3x. I want to know what is the general solution. And why is that the general solution? Okay. One thing to remember from our first day of notes, we're considering the cases where all of the coefficients are continuous and the first one never equals 0. So that's going to be true, but just make sure that you check that. By superposition principle, we know that y equals c1 e to the 3x plus c2 e to the negative 3x is also a solution. Now, you can probably guess that that's the general solution, but I want to know why that's the general solution. So what we've written down before, if we have a fundamental set, we have the general solution. In order to have a fundamental set, we need to have linearly independent solutions. So what we need to prove is that we have linearly independent solutions, which gives us the fundamental set. Fundamental set gives us the general solution. So how can we show that those two functions are linearly independent? What are we going to use? Wronskian. Okay, so we have to find the Wronskian. It's the determinant. E to the 3x, e to the negative 3x, take the derivative. So we get negative 3e to the 0 minus 3e to the 0, negative 6. What we care about is that does not equal 0. Okay, so what that tells us is that y1 and y2 are linearly independent. If they are linearly independent, then they form a fundamental set. The fundamental set forms the general solution. So ultimately, that proves that y equals c1 e to the 3x plus c2 e to the negative 3x is the general solution. Okay, generally, students forget this part. So what they'll generally do is find the Wronskian, show that it's not equal to 0, and jump to the solution of fundamental set, or jump to the conclusion of fundamental set. You can't do that. The Wronskian shows linearly independent, which shows fundamental set, which shows general solution. So please do not skip that linearly independent part. There still can be other singular solutions that will not be found from this. So there still could be kind of those oddball solutions that you're not going to find from the general solution. Do you remember which solution every homogeneous linear differential equation has? Y equals 0, but yeah. Yeah, y equals 0. Okay. We could stop here and do the same amount of notes tomorrow, or we could learn about Abel's theorem and then have shorter notes tomorrow. Okay, we're ready to stop?